folks, let's go over a quick understanding of FSK, an overview of the slides here. So FSK, we're going to use to send text. We're going to convert the text to bits, bits to tones, and then on the receive end, we're going to take the tones back to bits and the bits back to text. Alright, well, how do we do all this? Matlab was used to read in a text file, and it creates an audio wave file with 4 FSK tones. This is the FSK transmit text file, or M file. And then there's a receive file, the RX receive.m file, that is used to read in the wave file and decode the tones back into text. Now, to really use this with some hardware, this is the proposed idea. We have the transmit side, so you send the transmit wave file to a IQ vector signal generator. In my case, I sent it out at 151 megahertz, but you can put it at any frequency you want, low power. And then on receive, I tuned the SDR radio to the same frequency and recorded the IQ file from the SDR radio, which is also another wave file that that Matlab is then to process. So I said if we want to keep everything within a 10 kilohertz bandwidth, a good sample rate would be 11.025 kilohertz sample rate. Now this is a very important thing. Remember, with IQ sampling, the bandwidth of your signal is very close to the sample rate. Well, why is that? It's because you're dealing with two signals, I and Q. And the easiest way to think of them is I by itself has a bandwidth of Fs divided by 2, and the Q signal by itself has a bandwidth up to Fs over 2. And when you add them together, you get the sample rate. So it's very, very important. If you learn nothing else from this video, know that when you're working with IQ baseband signals and someone says it has an IQ sample rate of 11 kilohertz, the bandwidth of what you can transmit is going to be pretty close to 11 kilohertz. It's not going to be half. And that's because we're dealing with IQ. There's effectively two signals we're transmitting, right? If we only were dealing with one signal, then you're correct. The bandwidth would be half. But because we're dealing with two distinct signals with two distinct sample rates, the effective sample rate is the sum of them, right? So again, if someone says they have an IQ sampling of 1 megahertz, that means the bandwidth can be very close to 1 megahertz, not 500 kilohertz. That's a very important lesson. I hear that mistakenly said over and over, and I just thought we would correct that. Anyway, off the soapbox. So we want to do these. How are we doing this? Well, we'll limit the waveform to 128 characters. And each character will be 8 bits, so that's a total of 1024 bits in the transmission. Since we are doing 4 FSK, that means we have 2 bits per symbol. So that means we'll do 512 symbols in the transmit waveform. And we'll put a linear FM chirp at the beginning, and we'll use that mainly to detect when the signal is inbound. It's mainly for a preamble and sync detection as well. If we were just to put the bits here, it'd be very hard on the receiver end to know when is this starting. Yeah, you could look for a rising pulse and things like that, but a chirp is a clever way because now we can exploit the match filter to find this chirp first, and then we know once we find the peak, which will be right here, right, then we know the next 512 symbols is the start of the transmission. Pretty simple. Some details on this chirp. It's going to have a half a second pulse width. It's going to occupy 10 kilohertz of bandwidth. So its slope is going to be the bandwidth over the pulse width. And this is the value represent the waveform of the chirp in complex notation. It's j times pi times slope times t squared. And it's very important that t here extends from minus pulse width over 2 to positive pulse width over 2. That's the range of the time vector that's used to plug into this. And you'll see this in the Matlab code that I've posted. Alright, so the chirp waveform is going to have the chirp, and then there's going to be 300 samples of off time before we start the symbols. Why did I do this off time? That's to handle multipath, like I said. When you transmit this in the air, the compression may bleed over a bit, so that's why we put a pause time here. So in my case, I made it 300 samples of off time. Again, you'll see that in the Matlab code. Alright, well now we have all these bits, and we need to represent each bit by discrete tones. In my case, I used 4 tones. So what you want to do generally, the idea is if you know the FFT size, you want to pick the tones such that the tones will be in exact bins of the FFT. Well, how the hell do you do that? Well, you have to compute something called the hertz per bin, which essentially says when you take a 512 FFT, what is the hertz that's going to be in one bin? And that's this simple equation here. It's the sample rate divided by 512, and that works out to be about 21.5 hertz per bin. So every bin in the FFT is going to cover about 21 hertz. So the idea is that when you're picking these 4 tones, you want them to be essentially integers of this number right here. That's the idea. So in my case, I picked negative FB, negative FA, positive FA, and positive B as my 4 tones. And each of these tones we can represent by this mathematical equation here, where F0 is the corresponding tones up here that we're going to use, and this time vector is going to be a 512 length time vector. Again, the Matlab code shows that. Alright, just some gory math to how I got the tones. Again, if our sample rate here is 11.025 hertz, that basically means our range is going to be minus 5K to plus 5K. That's the range that we can put signals in, right? So this is how I figured out we could pick 4 discrete tones that would cover the bandwidth of 11 kilohertz. And these are the 4 tones right here. You got minus 4K, minus 1300, positive 1300, and positive 4100. So these are the 4 hertz tones that we'll be modulating based on what bit pattern we have. And the symbol waveform is going to be the tone signal, and it's going to have a 50 sample off time. Again, that's for multipath. And each tone is going to transmit 2 bits. Alright, that's the overview of the FSK. Again, all the details are in the Matlab script to see how it's done, but this is a high level of how we're transmitting this waveform and then receiving it. Now, if you don't have hardware, you can still use Matlab to create the wave file and then receive the wave file. But if you do have some IQ modulator and receiver, you can actually use this project for an actual demonstration. Many people I know have transmitted this up at 900 megahertz, 2.4 gigs, and you know, it's a way to get people to understand how do you actually implement these things in the real world. You know, this is way beyond a textbook describing high-level FSK. This is how do we actually go ahead and implement this? Now, this is no known standard. This is just something I made up, right? When you understand how something works, you can make the standard. We could have followed a standard, of course, and then some software out there could decode it, and then you would have learned nothing. This way, we'll make it ourselves and actually decode it ourselves, and hopefully we'll all be richly rewarded in understanding the nuances of digital communications. Thanks for watching.